This. Okay. All right. So the worksheet asks us to draw a sketch all the forces acting on the object using a free body diagram. And it asks us to represent the length of represent the magnitude of the forces with the length and the direction of the arrow vector. So let's do the first one. Object lies motionless. So it's just okay. So the first one, object lies motionless, so it's not moving. So that means any force that's acting on it should cancel all balance out altogether. So usually we just represent the object by a dot. Any object that has mass will have weight. So it will have a weight force. Weight force is always downwards. The object is supported by the surface, so it should have a normal force. Normal force is always perpendicular to the surface. Right? And normal force. Okay. There are no other forces in the vertical, only these two. And so the length of these arrows should be the same. So roughly, I hope in my drawing, they're roughly the same. There are no forces along the horizontal. It's motionless. It's not moving. Even if it didn't say that, yeah, so there are no forces along the horizontal in this case. Right, the next question, the object slides at constant speed without friction. So specifically stating that there's no friction. Constant speed, meaning acceleration is 0. That means the object is just moving in the same direction with the same speed. So again, easiest force to draw would be the weight force, and then the object is moving on a surface, so you again have the normal force as before. Now, how about the forces along the horizontal? So it's moving at constant speed. Newton's first law of motion says that if the object is moving with constant speed with the same speed in the same direction, then net force is equal to 0. So there should be no forces. The net force should be along the horizontal should be 0. And since the problem specified that there's no friction, then there should be no applied force as well. Because once you put an applied force, for example, you put an applied force to the right because the object's moving to the right, then that gives an imbalance of forces along the horizontal that will change the speed of the object. Because there's no friction force that will counteract this applied force. Right, so there shouldn't be any other force along the horizontal. In the third case, that's when the object slows down due to kinetic friction. So there's now friction there. So again, let's draw the two obvious forces first, weight force and normal force along the vertical. Yeah, in this case now there is kinetic friction. It's the friction when the object's moving. It opposes the object's motion, and the figure shows that the object is moving to the right. Okay. It's the object slows down. That means, there should be just one force that is opposing the motion of the object that makes it slow down. Right. So initially, the third case is the second case, but with friction. So there's the object is already moving. There's no applied force to the right. The object is just moving by itself, but then you put friction in the opposite direction that will slow the object down. So you only have this frictional force along the horizontal. Right? I hope that makes sense. Right, the next scenario is the object on the slope and there is no friction. So it's the same case as the second question, but except that the surface is slanted with a slope. Let's again draw the obvious thing. Weight force, it's always there. It's always downwards, regardless of whether your slope is flat or at an angle. And then you have the normal force. This time, your normal force is not vertically upwards because the normal force should always be perpendicular to the surface. Okay, so this is a rough sketch. So that's the normal force that's to the surface. Right. It slides, the object slides without friction. That means it's probably starting from rest and then it starts to move downwards. So there should be motion downwards along the slope. So if we do our parallelogram method, I should have drawn the normal force. Let me draw the normal force with a different color. Oh, my pen stopped working. Yeah. So let's say draw the, oh. See, that's the normal force. If we do the parallelogram method, so we copy the normal force, connect the normal force onto the weight force, and then copy the weight force, connecting that to the normal force, we should see a net force that is along the slope. Right, so that tells me that the lengths of my vectors are not okay. So that tells me that there should be a net force. There should be a net force that is along the slope, because this net force will cause the object to move downward. So if I draw the correct free body diagram with the correct lengths for the weight and the normal force, I should take into consideration the direction of the net force. So I should have a normal force. It's probably roughly that length. So that roughly, if I do the parallelogram method, just my pen keeps. If I do the parallelogram method, then roughly I should have, a net force that is along the slope. Right? Okay, does that make sense? But you only just need to draw the weight force and the normal force. Okay, so the next one, static friction that's preventing the sliding. So it's like question 4, except this time you need to add a friction force. So again, draw the obvious. You should have a weight force that's downwards. Okay, and then you have this normal force. It's the same magnitude of the normal force that you drew in question 4, except and that will assure you that the net force between the normal and the weight force will be along the slope, except this time you now add a frictional force. yeah, you know from question 4, the net force will be along the slope. So that's the net force along the slope. So the frictional force should be opposite the direction of the net force. So the frictional force should be along the slope, but upwards, yeah, towards uphill of the slope. Right. Does that make sense? Yeah. Good. And then question 6, object is suspended from the ceiling. Anything that has mass will have weight, and weight is always directed downwards. So that's almost always the obvious thing. And then you have the string that's supporting the object. Tension force is always directed away and towards, away and along the string. Okay, the object is not moving. So the tension and weight force should have equal lengths. Okay. Question 7 is like the example we saw in class, but this time, yeah, this was the, but this time the angles are equal. So we've already seen this in class earlier. So you have the weight force, always the obvious thing. Obvious force is the weight force. And then you have two tension forces along the string. Okay. But the angle is the same. So you would expect that the length of the two tension forces would be the same, so that their net force, the net tension force will be, yeah, so that you would expect that the net tension force would be directly vertical, counteracting the weight force. Net tension force, and we can say this is tension 1 and tension 2. So we'll just draw that neatly into our free body diagram. So you have tension, let's say that's tension 2, and the other tension with roughly the same length as tension 1. Yeah. Right, next one, object is motionless again. Let's again draw the obvious force here. You'll have the weight force that's going downwards. Right, so there are two strings connected to these surfaces. So again, we saw earlier, even if the surface, the vertical and horizontal surfaces are indirectly supporting the object, but there is a string between the surface and the object. So the correct force in this case would be the tension force along the string. And tension is always directed away from the object along the string. So for the horizontal string here, you should have a tension force directed to the right. And for this diagonal string, you should have a tension force that's diagonal, directed to the left. If you do the parallelogram method, you should adjust the lengths of these tension forces so that the parallelogram method, tracing out a parallelogram, the parallelogram method should give you a net tension force that is vertically upwards equal to the length of the weight force. So this is the net tension force, the black one. The purple one, let's say that's tension 1, and the blue arrow, let's say that's tension 2. So just drawing that neatly onto our free body diagram, you have the weight force that's downwards, you have the tension force along the horizontal, let's say that's tension 1, and then you have the tension force that's diagonal. Diagonal along the string. Yeah, it's just a rough sketch now. Tension 2. Yeah, and the net force between tension 1 and tension 2 should be directly vertical. All right. Okay, next, the object is motionless again, but there's a string that's connecting it along the slope. So obvious things, weight force, normal force, because the object is supported by this slope, this surface that is at a slope. So you have your normal force that is perpendicular to that surface, and then you have the string. So there's a surface here, but indirectly supporting the object. You have tension along this rope that's directly supporting your object. So tension force is directed away from the object and along the string. And if you draw the parallelogram method between the tension and the normal force, they should form a net force that is directly vertical. That's tension plus the normal force to oppose the weight force. Okay. So I think I've drawn, so you can see here my tension plus normal force that's directly vertical is longer than my weight force. That means I have to adjust the length of my normal and tension forces so that to have the correct length for this vertical tension plus net force. So I'll draw that in neatly in the free body diagram. So maybe I'll make my weight force longer in that case. And then I should have the normal force and the tension force. Oh, let me label normal force and tension force. Yeah, it's probably, yeah, but roughly the parallelogram rule of normal and tension should have this net force that's vertically upwards. So maybe I need to make my tension force a little bit shorter. Right? Yeah. So you do not need to draw the T-net on the diagram. So the diagram just contains the individual forces. I'm just drawing the T-net just to know the relative lengths of each of the forces, because then the T-net should balance out whatever weight force that you have. But in the end, your free body diagram should just have the individual forces. Right, so question 10, there's no string, so it's just surfaces supporting the object, so it's just normal forces present there. But again, the easiest force to draw would be the weight force, always directed downwards. Right, and then you have this surface on the left that's diagonal here that will provide the normal force. Your normal force should be perpendicular to this surface. Right, so that should be your normal force there. And then you have the surface below. This surface below here that's supporting your object, so that will provide a normal force. The normal force should be perpendicular to that surface. Normal force. Okay, oops. And the net normal force, if you draw the parallelogram for these normal forces, so now I can see, yeah. So if you drew your normal forces that way, then you can see that the normal force, net normal force, is not directly vertical. So that means you have to adjust the lengths of your normal forces to have a directly vertical normal force. like so. So that means I have to adjust actually the length of this normal force. Yeah. Right. So that if I do the parallelogram method, then roughly the net normal force, so the black arrow that's directly pointing out upwards is the net normal force. The combination of the two normal forces should balance out the weight force. If I draw my free body diagram neatly, I have the weight force that's downwards. I have this normal force that's just a little bit shorter compared to this normal force, like so. All right. Okay. Hope that's making sense so far. Yeah. So here, question 11, the object is moving to the right and slowing down, but this time you have pulling force, a tension force. So again, you have your weight force that's downwards. You have your normal force that's upwards. I'll just draw it with the same color because they are the same length right away anyway. And then you have, so there's an extra information here. It's slowing down. That means there's friction. So you should have, so you still have this tension force. Let's say you're pulling it via a string, or you can just put F pull, or you can assume it's via string, in which case that's tension force. And then you have, it's slowing down, so you need to have a frictional force in the opposite direction. Right? I'll skip question 12 and question 14. I'll do that last because that is related to our next lecture. We'll do the next question. The object is connected to the string. Again, you have the weight force and you have tension force. Okay, they should have equal lengths because your object is stationary. Okay. I'll also skip questions. So question 13 and 14 takes more than just the parallelogram rule, and that will be our topic for the next lecture. Right, question 15, the object is falling with no air resistance. So this is the free fall situation. And we said that in free fall, you always have gravitational pull, so you'll always have weight force, and there's nothing else acting on the object. It's just the gravitational pull that's causing the object to accelerate downwards. Okay, and there's no air resistance resisting the motion. So only one force in the free fall situation. So the ball is rising in a parabolic trajectory. I think there's extra information as well. Situation 17 and 18, neglect air resistance. So this is again a free fall situation. Even if your ball is tracing this parabolic path, you will only have one force, which is the weight force. In any free fall situation, you only have the gravitational pull acting on the object. And so it's the same thing for this ball at the top of its parabolic trajectory. So the question 18 is the ball being thrown up. Okay, and it's at the top, so your speed is 0, but even if the speed is 0, there's still a gravitational pull that will pull your object downwards, that will cause it to move downwards, as you've learned in the previous lecture with free fall. Okay. Right, question 16, it's a falling object, but it's not a free fall scenario because you have friction there. You're moving at a constant velocity. Newton's first law of motion, we learned, said that the net force should be 0 in order for the object to move with the same speed in the same direction, meaning constant velocity. So for this object to move with the same speed and 0 acceleration, you need to have a counteracting force And that's actually frictional force provided by the air resistance. Okay. Right. So you have two forces there, and they should be equal in length so that the net force is 0, and the object moves with the same speed. Right. Okay, so question 12 and 14, so we also run out of time. I'll do this in the next lecture. Yeah, you will also know, I'll just draw the free body diagram. But for the relative magnitudes, or the magnitude, that should be weight, W. So, but for the relative lengths of the vectors, we will talk about that in the next meeting, because the parallelogram rule sort of is a bit difficult to use in this situation. So you have your pulling force, you have the normal force, and question 12 means that it's moving at a constant velocity, so you should have a frictional force that will oppose the pulling force, so that the net force should be 0 along the horizontal. So that's the free body diagram, but the lengths of the arrows are not entirely correct in this case. We will talk about another method for finding the correct lengths of these arrows in the next lecture. And then for the last question, again, you have your weight force and your normal force, the usual ones. You have your pushing to the left downwards, so your applied force should be to the left and along the push. Okay. And then the object remains at rest is the extra information. That means you need to have a counteracting force to that push force, and that counteracting force is provided by a frictional force. Okay, right. So why the frictional force is along the horizontal, and why isn't it not directly opposite the push force? We will see that in the next lecture. It's the same case here. Why is the frictional force to the left? Why isn't the frictional force diagonal, directly counteracting the pull force? We will see that in the next lecture as well. But yeah, so let me just erase this wrong. It's not allowing me to erase, but yeah, so the correct free body diagram will be the frictional force in blue, not the frictional force in black, and we'll see why. We'll see that in the next lecture. All right, any question about the workshop or the lecture or the course in general before we end? Yeah. So yeah, the mastery test, it's lectures. There's a little bit technically speaking, it's lectures 1 to 4. You should be able to answer the mastery test with lectures 1 to 4, up to motion diagrams and kinematic equations. But just the last question, there's one question in the lecture that sort of uses the concept of free fall, of throwing an object downwards. You can still answer that because it's a graphical question, but it's just knowing that if you throw something upwards, the ball will go up and then eventually come down. So yeah, so it uses some concept of free fall, and that's why I would like to think that it's lectures 1 to 5, but it shouldn't be a very hard lecture 1 to 5 where you need to solve the kinematic equations of the free fall. Yeah, in any case, it's open book. You can refer to the lecture slides and the lecture video. Yeah, good. Any other questions? Okay. No, there's no specific layout. So the lab homework, if you watch the video, intro video, it says that you need to type your answer onto Stream, and it limits, to 250 words. I would accept a PDF scan of the homework page of the lab homework handout. So you can, I think from last year, I think Stream can accept a PDF upload. If not, you need to type your answer onto the text box there, but there's no specific layout. I just need to see those 3 questions there describing your experiment, your raw data, and your average speeds with estimated uncertainty. Yeah. Cool. All right, good. Any other questions? Yeah. You can always email me if you think of a question, especially during the weekend, just before the deadlines. If you're having trouble with the mastery test as well, technical difficulties, please email me as well, and we can look at solving your problem. Yeah, so any issues that you encounter with Stream or doing the mastery test or with the homework, please do email me, and we can find a solution for that. Yeah. Cool. All right. Just watching the chat box. I'm not seeing any more questions, and I'm quite aware it's past 12. Yeah. Yeah, unfortunately, I have to cancel the face-to-face workshop this afternoon, but yeah, fingers crossed. I'm pretty sure we'll have a face-to-face workshop next week. So have a good weekend, everyone, and I'll see you next Wednesday for the lecture.